The oceans of the world are littered with sunken ships, and for centuries, man has struggled to find a practical, economical way of underwater salvage. Since the beginning of time, mariners have struggled with rope, pontoons made from goatskin, used brute strength, and in later times, mechanical lift, huge cranes to raise sunken vessels. The technological revolution gave us almost unlimited power and plastics for flotation. The two stumbling blocks were operating at great depth and cost. But a brand new innovation has now removed those stumbling blocks and pointed the way to a new era in underwater salvage. The Booth, a 2,400-ton barge, went down in a storm off the Texas coast in 1969. It settled dangerously near a natural gas line, defying conventional salvage methods. And it became the first large-scale test to see if new ocean technology could conquer old problems. The new salvage system uses pressurized plastic spheres. It's called PSI for Pressurized Sphere Injection. The spheres are first pressurized on the surface, and the water forced out of the delivery tubes which shoot the spheres down into sunken ships. Each sphere shot down is a step toward achieving the buoyancy needed to raise a sunken vessel. The larger the vessel, the more spheres. As they shoot out of the delivery tube, the spheres float on their own, with the first ball forced out of the tube by those that follow. They're precisely counted as they go down, so that the exact quantity of buoyancy needed can be achieved. As the spheres enter the hull to be raised, they displace water, forcing it out and taking its place. Result, buoyancy. After enough balls have filled the hull, it starts to rise on its own. Phase 1 of the PSI process is complete, but the real secret lies ahead. As the hull rises, the water pressure decreases, and the spheres would rupture from their own internal air pressure, but for the fact that they bleed off the excess pressure through unique valves, the same valves the spheres are pressurized with. As the model reaches the surface, the air pressure in the spheres has been equalized and a stable condition has been reached. After the laboratory testing had proven the principle beyond doubt, test hardware was constructed and taken to the Bahamas for the first field tests. Cat Key was the site chosen for the tests. The test barges anchored and made ready. A 30-foot-long steel cruiser, the Humble, weighing 5 tons, was utilized. First holes were cut into the cruiser to sink it. The divers attached a delivery hose to the pressurization chamber and then lowered the hose from the tanks to the sunken hull. The hose was secured to prepare for the delivery of the spheres. Air flows out of the delivery hose as the tank is pressurized to equal the bottom pressure. The balls have now also been pressurized. And they're shot down into the hull of the Humble. Buoyancy is achieved, and the vessel starts up to the surface. The hull surfaced neatly and remained floating, held up by the buoyancy of the spheres. Extra tests using nets to secure hatchways or openings were run, a method invaluable for some types of salvage, and the nets proved themselves out as well. The PSI spheres demonstrated they're easily removable with a vacuum system, and they're reusable, a key to controlling costs. After these research and development tests had shown the concept fully successful, the decision was made to tackle a full-scale operational system. The first step, building a full-size pressurization device, the PUF. The operational system uses 11-inch plastic spheres delivered through 12-inch pipe, hose, valves, and fittings, standard sizes, and the 12-inch hardware was as large as could be practically handled by divers working at any depth. The 11-inch spheres are easy to handle, lightweight and air transportable when swift delivery is needed. A new plant had to be built to make the 11-inch spheres. The first step, putting the polyethylene raw ingredients for the spheres into molds. After the ingredients are mixed and set, the half of the mold is set in place and secured with clamping mechanisms. The molds are then placed in ovens for a slow cooking process. It's called rotational molding, and the molds are revolved around 2 axes simultaneously while the mold is being heated in the oven. The high-density polyethylene powder melts and forms a molten shell on the inside of the mold. The mold is then moved from the oven to a cooling chamber, where a water spray both cools the mold and solidifies the plastic. The mold is then opened, and you have a one-piece plastic sphere. The bottom of the molds are provided with threaded mandrels, which simultaneously mold a thread into the ball with a valve retainer, saving a step. The spheres are removed from the mandrel by screwing them out of the mold like taking a nut off a bolt. While still warm, the spheres are conveyed up an elevator into a storage bin, where they stay until the entire cooling process is completed, and the plastic is cured, thus acquiring its full strength. The spheres are then taken out of storage and run through the assembly process, where the rubber valve discs are inserted and the plastic retainer is screwed into place to hold the disc firmly. Here's the valve retainer in close-up on the right and the valve diaphragm on the left being manually flexed. Exactly what happens when air pressurizes the spheres before use, or air is bled out on the way up from the bottom. After the valves have been installed, each ball is tested in a pressure loading machine. They're shock-loaded real-time, almost instantaneously, to 125 pounds per square inch, to be sure there are no structural flaws that came out of the molding process, and that each valve diaphragm is properly seated. As the spheres emerge from the tester, the operator checks each valve to see if it's operating properly, and the balls then go into the final conveyor, to waiting containers where they're packed for shipment. The first full-scale test proves to be an agonizing battle of man against the weather, retrieving a sunken barge in midwinter, fighting water a few degrees above the freezing point. Rhode Island's Providence River, and it looks deceptively calm here. The PSI equipment is trucked in and moved into place on the dock. And then the snow hits. The mission, to retrieve a barge blocking the municipal dock. 2 previous salvage attempts had failed. The barge had sunk in 40 feet of water, 80 feet from the dock. Delivery lines out to the barge had to be rigged. The trial is not by fire, but by snow, ice, and sub-frigid conditions. Every conceivable kind of mechanical problem had to be overcome to get equipment to work in the freezing temperatures. The puffer was set up and made ready to pressurize the spheres despite the extreme weather. The huge baskets used to ship, store, and handle the spheres were unloaded on the dock. Delivery pipes were cut to size in preparation for placing them through the deck of the sunken barge. The divers had to wear heated suits to survive in the frigid water. Water temperature, 34 degrees, as the divers enter the murky river to emplace the delivery tubes. Cranes go to work, lifting the delivery tubes, and they're directed and eased down into the proper position. The delivery tubes are lowered into the water to the divers waiting on the deck of the sunken barge. The balls were then loaded using vacuum devices into the upper end of the pressurizing unit. They shoot through the flexible suction hose and emerge pressurized to be discharged from the lower end of the pressurizing unit into the barge. And the entire system worked under the worst possible conditions in its first real large-scale test. The diver takes the easy way up, riding the barge to the surface. Since Cyclo then didn't have enough buoyancy available to raise the entire barge at one time with PSI, one end of the barge was raised with the pressurized spheres, and then the job was finished by pumping out the other end of the barge. Rhode Island proved the system was ready for its first full-scale offshore salvage operations. 40 miles off Sabine Pass, Texas, the pipe-laying barge, the Booth, had been sunk for more than 2 years. The PSI buoyancy system was delivered to the Sabine Pass docks by truck and then loaded aboard a barge in preparation for the salvage operation. The tug and the barge get underway, heading out into the Gulf of Mexico for the site of the sunken barge. Arriving at the wreck marking buoy, they anchor over the wreck to get ready for the job. First step, a series of sessions between divers and engineers on how to proceed, and most critically, where to start cutting the holes for the delivery tubes. The Booth is 246 feet long, and as the divers get ready to go over the side, they know it's going to take plenty of time locating and laying out the holes for the tubes before they can begin cutting the holes in the deck of the Booth. After cutting the holes, they have to work their way into the hulls inside to be sure it's clear underneath and around the hole, so the spheres can work their way into each compartment. If it's not clear, they have to do additional cutting. The divers make a final inspection of each hole as they swim through the hull. Then egress through the same holes the pipes will be placed in.
Okay, crane's coming down to you.
The delivery tubes are lowered away, go under, and are then guided down 50 feet to the divers on the deck of the sunken barge.
All stop.
All right, come up.
Taking up on the cables.
Down.
Lowering down.
The water is murky, the bottom stirred up by Gulf storms, and the work backbreaking and time-consuming.
All right, pick up some more on them.
All stop.
Come on up.
Coming up easy on the cable.
Come on up.
After the delivery tubes are set, the divers surface and the final phase is ready to get underway. The delivery line from the pressurizing unit down to the tubes below is attached. The plastic spheres are vacuum loaded into the pressurizing unit. Then the balls are pressurized and shot down into the barge. The counter tallies each ball sent down, enabling engineers to tell exactly how much buoyancy they have in any compartment at any given time. The booth is about ready to come up. The first sign that it has succeeded are the bubbles, excess air bleeding out of the spheres as the booth starts up with the air bubbling to the surface. The bow breaks surface first, followed shortly by the stern. Now the entire barge is floating on its own, supported only by the plastic spheres. Next step, getting the booth back to port safely. A tugboat has been standing by and moves in to make fast its tow lines, then moving off to take the slack of the tow lines. The tug puts a strain on the line, gets underway, and the booth slowly swings into position. Within a few minutes, the barge pulled by the tug is making 5 knots, heading for Sabine Pass. The booth back in Sabine Pass, tied up in a slip. The water has been pumped out and she's safely moored. The key now is retrieval, recovering each of the 11-inch PSI plastic spheres. They can be used over and over again, unlike almost any other salvage system, which means lower costs. Total time for retrieving all the spheres is a few days. The barge is then temporarily patched to retain watertight integrity and towed back to Morgan City, Louisiana. The home base of, before a Gulf storm, abruptly changed her direction and destination. The real challenge is not the crystal clear sunny reefs of the Bahamas, but in the backbreaking dirty work of everyday salvage, where the sky above masks the mud below. Untold thousands of ships have sunk over the centuries and now rest on the bottom. Scores go down every year, an enormous loss and an incalculable pollution menace when they carry oil or chemicals. Man has battled the seas since time began, and mostly lost when he had to work beneath their surface. But technology now points the way to a new future in underwater salvage.